Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. My name is Awaludin Nurmianto. I am lecturer on the Department of Environmental Engineering, Universitas Islam Indonesia. And today I will lead you to join in our international lecture series in the subject of unit operation and process in environmental engineering. Before we start, please allow me to greet our special lecturer today, Professor Yong from National University of Singapore. Hello, Professor Ang.
Hello.
Hello.
Good afternoon, everybody.
Okay, good afternoon. I'm very pleased to have you, Prof. I hope that pandemic will end soon, so we can have opportunity to meet each other in Yogyakarta. It's the royal city of Indonesia, that the city that's still ruled by the king until today, Prof.
I see.
Okay.
Hopefully, yes.
Okay, hopefully. Yeah. And then, okay. On behalf of the Environmental Engineering Department, I also want to express my gratitude to you for accepting our invitation on the international lecture series in our department. I believe that your expertise in the field of wastewater treatment can give us enlightening insight, especially to my student on advanced process in water and wastewater treatment, like wastewater recycle or wastewater reuse in Singapore. Okay, as we can see here, Professor, we have more than maybe 100 participants from our student who takes the unit operation and processes in environmental engineering class. Now they are on the fourth semester or in the second year of bachelor degree. And then we also have maybe around 30 people who join us on YouTube because this class also stream on YouTube is as our commitment from Universitas Islam Indonesia to spread the knowledge and become rahmatan lil alamin, or give mercy to the world. This is our motto, Professor. Okay. But before we start, let me kindly remind you that to all of my students that you should turn on your camera, okay, during the session. And during the session, you can leave the question on the chat box. Okay, if you have any question, you can leave the question typing in the chat box. Or you can raise your hand and I will give you an opportunity to directly ask to Professor later in the discussion session. Yeah, it is clear enough? Okay, yeah. Okay, all right. Without further ado, please welcome Professor Yong, our special lecturer for today. Professor Ang, please welcome.
Okay, good afternoon, everybody. First of all, I'd like to thank Professor Awaludin Nurmianto for inviting me to give this 2.5 hours lecture to the students and also other participants through the YouTube. So it's a great pleasure to give this presentation. So today there will be two parts to the lecture. First, I will talk about the Singapore water strategies management, including wastewater treatment water reuse to solve water security issues for Singapore, both currently and also in the long term, especially we face unpredictable weather or climate change due to this global warming, right? So this is part one of the lectures. Part two of lectures, I will talk about membrane bioreactors and also and the nutrient removal, also looking at energy recovery. Okay, so two parts to today lectures. So we'll have a small break in between before I go to part 2 after I finish this part. All right. Now, so in terms of Singapore, I think many of you probably know Singapore very well. So Singapore is a small island state, and in terms of the land area is only 721 square kilometers, and we have a population of about 5.6 million. Now, although this island is a very small country, nevertheless, if you look at the average annual rainfall, it is more than 2 meters per year. So if you look at the amount of rainfall that we have, it is more than sufficient to provide the water required by the country, both for the human consumption or industrial usage. Now, in terms of water demand is about 1.9 million meter cube per day. Now, although we have so much rainfall, but unfortunately the land area is too small. There is insufficient area for storage. All right. So if you look at in terms of the world ranking, Singapore was ranked first among the country at the highest risk of high water stress in 2014. So when you say water stress, what does it mean? It means that a country receiving less than 1,700 meter cube per day, per year, per person from the natural rainfall or from the river. So that is how it is being defined as water stress. All right. So, but nevertheless, Singapore doesn't face the issue of water scarcity. Okay, so it has been a long journey because before Singapore can achieve sufficient supply of drinking water. So if we look at Singapore in the 1960s, we find that Singapore at that time is just before independence in 1965. You find that the waterways in terms of Singapore River, Kallang River, it was heavily polluted with wastewater and also improper discharge or uncontrolled discharge of sewage into streams and rivers. And these rivers and streams become an open sewer system. So with that, you have very polluted water bodies, all right, and that give a challenge in terms of using river water as a source of drinking water. Now, during that time, we also see very frequent seasonal floods due to areas where, especially in the downtown area or Chinatown area, where it is low-lying areas, and that's that flood occurrence intensified when the rain coincide with high tides. Okay, so seasonal flood is one of the major challenge. Now, if you ask me, do we still face a flash flood nowadays? I would say once in a while we did encounter that, and we can attribute that to blockage of waterways, and that eventually can be resolved. All right. So I'll talk a bit more about that and how Singapore can go about solving these low-lying area flooding issues. Okay, and the other challenge is open sewer poor sanitation. And at that time, 50% of the population was served by sewage network. The other 50% depend on night soil collection. So sometimes you hear this word called night soil. What does it mean? It means that it is like soil in the night. What happened is that this night soil system it originated very much from Japan. That is where you have a toilet system served by buckets, and then the workers will come in the night to collect them for treatment. Okay, so that end up it's known as night soil collection. All right. Now, but present day today, Singapore is in terms of the water body is well managed. It's very clean, and this is Singapore Marina Bay, and right at the mouth of the Singapore River and Kallang River. So on the right hand side is the Singapore River, where it joins, okay, towards this Singapore River here, join to the Marina Bay, and on the left extreme side is Kallang River. Okay, and these two rivers merge together in this Marina Bay area, and right now there is a dam right at the river mouth, where the whole bay area has become a freshwater bodies. And these freshwater bodies serve as one of the drinking water reservoir. So it is, I would say it is the one and only reservoir in the cities in the world. Okay, so of course, with that, people will be wondering, are you sure this drinking water is safe for drinking? How about all the surface runoff from roads? How about tire fabrics, all these particles, right? How do you ensure this water is safe for drinking? Okay, so I'll talk about it, what kind of treatment system was implemented in order to make sure this water from this Marina Bay is treated for safe for drinking, right? Now, so water, of course, we know water is a necessity. It is a survival for individuals and for countries. And so the late first Prime Minister, Mr. Lee Kuan Yew, did mention this during Singapore International Water Week in 2008. He said that water dominated every other policy. Every other policy had to bend at the knees for water survival. So these words highlighted the importance of water for Singapore as a national priority. And likewise, it is certainly so for many, many other countries. So we hear about in history, countries go to war because of water scarcity, water quarrel challenges, right? So certainly solving water scarcity issue is of national priority for Singapore and also for many countries in the world. Now, in Singapore, the water management is basically handled by a single ministry and single agency, right? So under the Ministry of Environment and Water Resource, right now they have changed the name, Ministry of Sustainable Environment, okay? So under this government agency, there are three different ministry. Under this ministry, there are three different agencies. One is the National Environment Agency that look at the land issues, clean air, and public health. Now, Public Utility Board Singapore will handle all issues related to water, including wastewater. So they look at used water collection, used water treatment, water treatment for drinking water supply, and including stormwater drainage system. Now, the third agency under the ministry is the Singapore Food Agency. And this food agency is to ensure and secure, to achieve a secure supply of safe food. And the focus now is trying to increase the local Singapore food production. And there's a target of 30% food supply in Singapore is produced locally in Singapore by 2030. So this is a very challenging goal, right? Now, so as I mentioned, Public Utility Board Singapore will handle all used water, all right? And that is important because you will see that used water is now considered as a resource, not only as a source of water we use, but also like resource recovery, including energy or even phosphorus nutrient, right? Phosphorus as one of the nutrients for recovery. So it is good that you have one agency to handle all issues related to water, right? So that it can achieve a consistent policy, right, to achieve water security for Singapore. Now, so of course, all of us know very well this climate change. I would say climate crisis has created a huge challenge for every country, I would say for the planet Earth. And we hear a lot of news about severe flooding and also a very severe drought. And now, how about Singapore? Okay, Singapore certainly is going to face challenges like dry spell. So in the past 10 years, there are incidents where Singapore experienced pretty long duration of drought and then no rain. Okay, and then of course, in terms of Singapore, we haven't really encountered water shortage issue because Singapore has implemented desalination and water recycling. And during that period, we desal plant and the new water plant were operating at full capacity to meet Singapore water needs. So although we met dry spell in the past, but the general public did not experience any shortage of drinking water. So we can see that water reuse, desalination will become, in my opinion, will become a very powerful alternative source of water supply for many countries in the world. Of course, when you talk about desalination, seawater desalination, certainly it is only applicable for countries or places near to the coastal region. Right? But water reuse is certainly can be practiced anywhere in every part of the world, as long as there is a source of water. Right? As a source, because you talk water reuse, first of all, you must have water. If you are in the middle of the desert, there's no source of water, I would say that is not a place for human habitat. Right? So as long as there's a source of water, you can recycle and use this water multiple times. And that is water reuse. Now, the other challenge that Singapore has faced and likely to face more in the future is plankton bloom. Okay, due to a global warming, the increasing of water temperature, seawater, water bodies, the temperature of water bodies. So likely of plankton bloom, algae bloom is going to more severe and occurring more frequently. So of course, what will that implication? The implication will be on water treatment, because algae plankton load will be much higher. So in terms of water treatment plant, your particle loads due to this algae will increase. So in terms of the cost of treatment will likely to increase. And if you talk about seawater desalination with algae bloom, you'll find that the treatment plant will face more challenges in terms of dissolved air flotation loading, and also on membrane fouling, potential membrane fouling. So these are topics that Singapore is looking into, finding solutions or operating protocol to solve issues that are likely to happen in the near future. All right. Although another issue is a very short period of heavy rainfall, so that caused a major flash flood in, especially last, I would say 2 years ago. All right, there was quite severe flash flood in Singapore. All right. So now, moving forward, of course, Singapore will likely to encounter very erratic weather instead of heavy rainfall or dry spell. Now, of course, temperature will increase moving forward, and that will bring about, like I mentioned earlier, algae bloom, plankton bloom, and of course, sea level rise is another issue. So likelihood Singapore will follow what the Netherlands has done in the Philippines all along this building dike, building pumping system, coastal protection system. So I would say there are still solutions, just that it's going to be very costly solution for Singapore or countries that are in the low-lying areas. Now, in terms of Singapore water demand, it is foreseen that by 2060, the amount of water usage will double compared to today, and the percentage in terms of industrial or non-domestic usage will increase from 55% to 70%. So what does that mean? Singapore has to look at solutions to increase water supply moving forward. Well, at the same time, if you look at Singapore's options, you find that there are little options for Singapore. Okay, I'll mention that what is the strategy for Singapore later on. All right. So the challenge for the utility is that we try to achieve energy efficiency, all right, so that we can cut down energy consumption for our desalination or new water plant, while at the same time maintain the biomass or sludge footprint. So you'll be wondering, what do you mean by that? Because, for example, in wastewater treatment, I believe everyone of us know very well, the primary treatment system is activated sludge process or biological process. So during that treatment process, we will produce biomass as an alternative, not as a byproduct of the treatment process. So what do we do with this biomass? Of course, a lot of countries can say, I will convert biomass to fertilizer if there's no heavy metals or other toxic compound inside this biomass, this sludge. So certainly you can treat it, and then as long as you get rid of the pathogens, you can apply for agriculture as a fertilizer. But in Singapore, we don't have agricultural farmland. So for Singapore, is that all these biomass are being dried and then incinerated, and then you will land up in the landfill. Okay, but Singapore has only a single landfill, which is the Pulau Semakau, and the lifespan of this landfill is probably by 2040. So the challenge for Singapore is how can we reduce the amount of solid waste going to the landfill so that we can extend the lifespan of this one and only landfill in Singapore. So that is a target for Singapore, Public Utility Board, to maintain or reduce the sludge production. So of course in Singapore, the researchers are exploring, can we reuse this sludge, for example, producing biochar, or put it into construction materials. So all these approaches are technically viable. Okay, means it can be done technically. However, the cost is today, it is not low. Okay, because if you want to produce into biochar, means that there's an energy input, right? And you want to add it into concrete, there's a incineration. I mean, the heat is required for all these treatment. So this is the challenge. Okay, how to achieve a low cost reuse of these sludge. So if you look at Singapore's strategy, how do we achieve water sustainability or water self-sufficiency? So the idea is to capture every drop of water. So Singapore, currently about 2/3 of the land mass are all converted into catchment area. Okay. But of course, there's a limit to how much you can capture because of the limited land space, right? Land mass. Now, the other approach is reuse water endlessly. So this is talking about new water, all right? And then the third option is to desalinate seawater, all right? So Singapore today has a diverse supply of 4 different sources. So right now you can see here, this diagram, we have only 3 sources. The 4th source is water supply from Johor Bahru, Malaysia. Okay, so right now Singapore has a contract with Malaysia, which will expire by 2061. So by then, if the contract cannot be renewed, then Singapore has to depend on these 3 strategies to achieve self-sufficiency in terms of water supply. Now, if you ask me, can we achieve that? Certainly yes, because desalination is can be done, but the only issue is that it comes at a cost, right? So right now, seawater desalination energy consumption is about 3 to 5 kilowatt-hour per meter cube. This is I would say rather high compared to fresh water from the river or from groundwater. So certainly we can build more desalination, but we have to pay. All right, per meter cube right now in Singapore, the cost of producing a desalinated water for each cubic meter will probably cost about $1 US, about that. Right? Especially with the energy cost increasing over the last 1-2 years, I believe the cost will increase substantially. Right? So right now, Singapore enjoy 100% potable water at tap and also 100% sanitation. Now, like I mentioned earlier on, PUB manage the complete water cycle. Right? So in this diagram, you can see that in most city, okay, you get your fresh water from rain, you got from storm water, go down to reservoir, right? And of course, many countries use groundwater as a source of fresh water. And in Singapore, we take this this water from this 17 reservoir, go through treatment of water, okay. And right now, Singapore have 8 waterworks, inclusive of Johor River Waterworks, and then 2 of them in Johor Bahru. And then after that, you send this as a potable water to household industry. So as the industry household use this water, we produce wastewater, we collect them, then we treat it at wastewater treatment plant. Right. So typically, this wastewater will discharge to the sea, right? And then it depends on the natural water cycle as a source of drinking fresh water. So right now in Singapore, this used water is then go through advanced treatment process, including with membrane filtration, reverse osmosis, ultraviolet disinfection, and we produce used water for direct non-potable usage. And then part of it, a very small percentage of it is being discharged to the 17 reservoir. And that is known as indirect potable use. So right now in Singapore, if you turn on the tap water, about 5% of the water is from recycled water. Right? Now, the other route is from sea, we take it from desalination and then as a source of fresh water. I mentioned Singapore have 4 taps: desalinated water, new water, imported water from Johor, here, and water from local catchment. Okay, so Singapore catchment has this type. This picture show the map of Singapore. So basically, 2/3 of Singapore is already converted to water catchment area, except the western region, the Jurong area, which is a heavy industry region. So that area is rainwater is not being collected for as a source of potable use. If you look at Singapore, the central region, where is the Macritchie Reservoir area, where is forested area. So these are the only protected catchment. The rest are considered urban catchment. All right. And then I mentioned earlier on, Marina Reservoir is the first reservoir in the city, collecting rainwater from highly urbanized catchment. And mentioned earlier on, Singapore gets substantial amount of water from Johor, Malaysia, and there was 2 contracts. One is already expired in 2011, so the second contract is until 2061. Okay. So in 2011, there was 1 waterworks hand over from Singapore to Malaysia. Now, so I mentioned water reuse is a very important aspect for Singapore as an alternative source. So to do water reuse, certainly the collection system is crucial. So Singapore collect its wastewater from Singapore through 2 deep tunnels. The first DTSS stands for Deep Tunnel Sewage System. So phase 1 was completed in 2008, which collected the eastern part of Singapore, the green sewer line. So it collects all the wastewater from half of Singapore all the way to the eastern side of Singapore with the Changi Water Reclamation Plant. So it has a capacity of about 800,000 meter cube per day. Okay. And then to the northern part of Singapore, there is Changi Water Reclamation Plant, which is when I say reclamation plant, it refers to wastewater plus reverse osmosis process, a new water plant. Okay, Changi Water Reclamation Plant. So northern part is a small plant, it's about 145,000 meter cube per day. Now in the west, there is this Tuas Water Reclamation Plant, which is currently under construction, will be completed by 2025, 2026. So this is about 800,000 meter cube per day. And you see that there is this gray line. This is the Deep Tunnel Sewage System phase 2, right, which runs about 40 kilometers to collect develop the other half of the Singapore wastewater towards the Class Water Reclamation Plan. Right. Now, in terms of used water treatment, so this is the overall process for the wastewater treatment plus for the wastewater treatment. So all this wastewater will connect through from the deep tunnel sewer system. After that, it will go through pumping station, go through headworks, very traditional, similar to all big wastewater treatment plant in the world. After that, go through primary sedimentation. After that, okay, normally most plants will use activated sludge process, comprising the aeration tank plus secondary clarification. Now, right now in Singapore, progressively, most of the plant has been converted to membrane bioreactor. So basically, membrane bioreactor comprises of aeration tank and membrane, either ultrafiltration or microfiltration, to replace the secondary clarifier for solid and water separation. Right? So membrane bioreactor, in the next part of the lecture, I will go through the details. What is it about and the advantages plus the disadvantages. Right. So this after the biological treatment, all right, membrane bioreactor. Okay, and then this on the top figure where you see there's a bioreactor secondary sedimentation. This is the conventional activated sludge process. So Singapore do still have some activated sludge process, but more and more of the plant are converted to membrane bioreactor. Okay, and the main driver here is that the membrane bioreactor can have a higher capacity with the same footprint, so that you can increase the treatment capacity and produce suspended solid stream water that you can actually go directly into reverse osmosis process without another ultrafiltration or microfiltration. But if you have the activated sludge process after secondary sedimentation, when you take this secondary effluent, go to a new water plant, you will have to go through the UF and MF pre-treatment before the reverse osmosis process. Okay. So this is the key process, the biological process for wastewater treatment. Now, with this process, you find that it produces biomass, primary solids, plus waste-activated sludge solids. And then what Singapore do is you go through a thickening and then go through anaerobic digestion. And anaerobic digestion, you have about 30 days of retention time, and you produce biogas for electricity production. Okay, and then the water sludge, okay, will then go through drying, and then the dry sludge will send for incineration. Okay, so this is how the overall process of wastewater treatment in Singapore. Now, let me show a video of the deep tunnel sewer system.
So we cannot hear the voice, Professor.
You cannot hear the sound. Okay, let me hold on.
Okay.
Let me see. Let me how to do sound. Hold on. Let me check the sound source. Maybe okay. Let me try again. See whether.
It's the eastern part of Singapore and was completed in 2008. It consists Singapore's deep tunnel sewerage system, DTSS, was a vision conceived in the 1990s. It was designed to provide a cost-effective and sustainable solution to support Singapore's long-term needs for used water collection, treatment, reclamation, and disposal. DTSS Phase 1 serves the eastern part of Singapore and was completed in 2008. It consists of a conveyance system made up of deep tunnels and link sewers, the Changi Water Reclamation Plant, and its outfall. Phase 2 will extend this deep tunnel system to the southern and western parts of Singapore. It will have a conveyance system made up of link sewers and deep tunnels comprising of a south tunnel and an industrial tunnel, as well as the Tuas Water Reclamation Plant, known as Tuas WRP. By interlinking with Phase 1, DTSS Phase 2 will complete the used water system to serve Singapore for the long term. Kranji WRP remains to the north as part of the 3-node used water system. How does the process work? Used water will be channeled from the existing network to the link sewers and into the south tunnel via drop shafts. The used water then flows by gravity along the south tunnel, which will run underneath major roads. It is then conveyed to Tuas WRP for treatment. There, advanced treatment technologies will purify it into new water and industrial-grade water for reuse. The integrated new water production facility at the Tuas WRP will boost new water supply. Any excess treated effluent will be discharged into the sea in an environmentally responsible manner. The South Tunnel serves as a cost-effective superhighway. Built at a gentle gradient, used water is transported entirely by the force of gravity before being pumped up at Tuas WRP. This removes the need for multiple intermediate pumping stations, eliminating the risk of used water overflows. Previously occupied land can then be freed up for higher value developments. The South Tunnel, which ranges from 3 to 6 meters wide, will mainly run along the Ayer Rajah Expressway. Constructed with tunnel boring machines, the South Tunnel lies deeper than some of the underground subway lines and even crosses beneath the seabed at Tuas Bay before reaching Tuas WRP. One construction challenge lies with the variable soil conditions and existing facilities. The conveyance system will cross under existing tunnels and pass through sedimentary rock with weathered water course channels and soil-containing sand pockets. Construction will be carried out with minimal impact. The Phase 2 conveyance system will also feature a complementary secondary liner with HDPE lining to protect against corrosion. One of the key features of the South Tunnel is its advanced sensing capabilities. Embedded on the primary lining, fiber optic wires are installed along the entire length of the tunnel. This monitoring system checks the structural integrity of the tunnel without the need for physical inspection. The fiber optic wires also allow engineers to pinpoint the section that requires isolation for human access in the event of repairs and emergencies. Used water will then flow through the tunnel uninterrupted via an alternative path. The conveyance system also features air jumpers and odor control facilities located strategically at shafts along the South Tunnel. They treat odorous air that may be expelled upwards. Air jumpers act as forced ventilation. They are designed to push odorous air back down into the tunnel to be treated by downstream odor control facilities. When the Tuas WRP is operational, existing Ulupandan and Jurong WRPs will be phased out, freeing up land for higher value development. In addition, advanced technologies at the Tuas WRP will improve its energy efficiency and reduce cost and manpower. The Tuas WRP design promotes energy efficiency. By building upwards, it has a more compact land footprint as compared to conventional WRPs and allows for natural ventilation and lighting, as well as easier access for maintenance. One advanced technology is the membrane bioreactor process, which replaces the conventional bioreactor, secondary sedimentation, and microfiltration and ultrafiltration stages, thus streamlining the used water treatment and new water processes into one. This provides space savings while generating a higher quality effluent for discharge into the sea. The plant will be the largest membrane bioreactor facility in the world, treating 800,000 cubic meters of used water per day. Another technology implemented at Tuas WRP is the thermal hydrolysis process, which will reduce the space required for biosolids treatment and increase biogas and energy yields. Tuas WRP will be co-located with the National Environment Agency's Integrated Waste Management Facility, IWMF, to reap the potential synergies of the water energy waste nexus, maximizing energy and resource recovery. For example, the food waste received at IWMF will be pre-sorted and then digested with sludge using twice WRP's digesters, producing biogas. The resulting biogas and sludge are then fed back as a fuel source to IWMF for incineration. Electricity generated at IWMF is then supplied to twice WRP for its operations. Besides process synergies, the two will share common facilities like the admin building and car park to further optimize land use. The co-located facility is compact, resource efficient, and the first of its kind in the world, planned from the ground up. DTSS Phase 2 is envisioned to be sustainable, resilient, and cost-efficient. To be ready by 2025, DTSS Phase 2 will be completed in stages through multiple tender contracts. With its completion, the deep tunnel sewerage system will play an integral role in Singapore's diversified water portfolio, creating a sustainable used water management system for our country's future.
Okay, so just now the video is introduce you about the DTSS Phase 2 and also the upcoming Tuas water reclamation plant co-located with the integrated waste management system, IWMF. So, okay, coming to new water, as I mentioned earlier on, after the used water are being treated, okay, and then you go through microfiltration or ultrafiltration before you go through this reverse osmosis process, followed by ultraviolet disinfection to produce this high-grade reclaimed water. So this in Singapore is known as new water, which is a high-grade reclaimed water. So mentioned earlier on, new water is primarily used by the industry as cooling water, as processed water, and part of it is added to Singapore, the 17 reservoir, to blend with the raw water as a source of drinking water. It is called as direct non-potable, indirect potable use, right? So new water plant right now in Singapore, we have the Kranji, we got the Bedok, we got the Changi, and Ulu Pandan. So in the future, there will be these Tuas and new water plant, right? Now, so of course, one of the key questions that a lot of people will ask is that, is this new water safe for drinking? Right? Because you look at new water is recycled water from wastewater, go to microfiltration, ultrafiltration, go through reverse osmosis, and then ultraviolet disinfection. So the challenge here is that, is it safe for drinking, right? So of course, the key is lesson from what other country has done. And then Singapore has done demonstration plant study. We have a very comprehensive sampling monitoring program. And in the earlier study, we also have health effect studies. So if you look at recycled water, if you look at what other country has done, so you see that the first country that implemented quite extensively is on water reuse is in the US, in Southern California, in I would say it's called LA, San Diego area, right? So at that time, there's this called Water Factory 21. Basically, they go through the same process, but the water is being used to recharge into the groundwater, recharge to the ground to supplement the groundwater, and at the same time create this seawater barrier, because you must make sure the groundwater is at an ample supply, otherwise the seawater will have intrusion issue. So your groundwater will become salty, dry, brackish, right? Because if your water uptake from the ground is too high than your freshwater supplementation, then you will have seawater intrusion. So in the early days, 1970s, there's this Water Factory 21. And they go through the same reverse osmosis process, produce this high quality our water, and they recharge into the ground as a groundwater supplement. Right? So that has been done long time ago. So certainly it has been proven to be working. And then in Singapore, before we started the new water in the early 2000s, there was an extensive study, including a demonstration plant, okay, and to demonstrate, and then first of all to produce enough water for laboratory scale study on the health impact, and then at the same time to gain the operational experience. Okay, so that new water demonstration plant was run from 2000 to 2013, and it's the capacity about 10,000 meter cube per day, which is quite sizable. So we'll test for reliability, robustness, and then to gain experience through the demo, so that you can incorporate this problem encountered into the design of the full-scale plant, and then help to understand and address concerns like damage to membrane by hypochlorite, for example. So in terms of sampling and monitoring program, until today, the Public Utility Board conducted regular extensive monitoring, including 293 water quality parameters, more than 100 specified by US EPA and 122 specified by WHO. And during this study, we conducted a most comprehensive water quality study of clean water. Right? And then this parameter include this very classical water quality. And the additional thing that they study is to look at synthetic and natural hormones, which we call it an emerging contaminant, or EDC, okay, on endocrine disrupting compound. Okay, so that was also being studied extensively, and also look at microbiological water quality parameter study. So this study, anyway, these are all the various type of category of test parameters. Right, and eventually there are 293. So you can see the emerging contaminants to consider 49 parameters. So in total, there are 293 parameters monitored consistently, including during the studies. Right. So of course, there are important practices like good laboratory practices, qualitative analysis, quality control. Make sure you have updated and effective and ethical protocol, and then good quality accurate data for analysis, training, and troubleshooting. So to date, more than 170,000 tests have been conducted on samples from treated used water and new water. So the new water is consistently meeting the latest requirement of US EPA, National Primary Secondary Drinking Water Standard, and the WHO Drinking Water Quality Guidelines. Right? And I mentioned earlier on, in early 2000, there was a 5-year study looking at the health impact. Okay, so in this study, mice and fishes were being, these two animal species were being studied for short-term and long-term health effects, looking at the long-term toxicity and carcinogenicity. So based on that study, it was proven that the new water indeed was very, very safe as a source of drinking water. Now, if you ask me personally, I would say certainly reverse osmosis water is very high quality. It is, in fact, much better than the typical tap water in Singapore. Okay, and in fact, reverse osmosis water is too clean. If you're consistently drinking RO water, it might be not good for your body. Okay. In fact, there was some study done in the early 80s in the Eastern Europe, where they found that those countries or area where most people consume reverse osmosis water, they has higher cases of cardiovascular disease, okay, because of lack of mineral. So, so this is one of the key concerns. Okay. So that's why in Singapore, desalinated water, actually they add calcium into the water, okay, to make sure the water is not corrosive, and also to make sure there are certain minerals in the water. Now, this health effect study, this strain B663F1 was used for the study, and that was a partnership between NUS and the EPL in experimental pathology laboratory in the US. So through the mice studies, multi-generation of mice, it was proven there's no long-term carcinogenic effect. And then the fish studies, okay, also demonstrated no long-term carcinogenic or estrogenic effects. All right. So I mentioned desalination is another important source of drinking water. So right now, Singapore have 5 desalination plants. Sing Spring desal plant, 30 million gallon of water per day. Then you got the Thrusday, all right? And then there's a third one, Tuas desal plant, also 30 million, which was completed end of 2017. So there are 3 desal plants in the western part of Singapore. Now, then Jurong Island, then the 4th desal plant is Marina East desalination plant, which is also having a capacity of 30 million gallon of water per day. It was completed in 2019, end of 2019. Now, right now, the 5th one was just commissioned about 2 months ago, okay, in Jurong Island. Now, I want to highlight this 4th plant, which is Marina East plant. Okay, it is located right beside the Marina Bay. Okay, so this plant is very interesting in the sense that it was designed to treat 2 types of water. One is the regular seawater. Okay. Now, just like I mentioned, how do you ensure the fresh water from the Marina Bay is safe for drinking? Okay. To achieve that, the Marina Bay water actually is being treated by the Marina East desal plant. So this desal plant serves either taking seawater for treatment or from the fresh water from Marina Bay go through the reverse osmosis process to produce a high quality RO water. So this is the treatment protocol to ensure that this Marina Bay water is safe. Basically, it's RO treated water. Okay. So this is the 4th desal plant. It's designed, built, owned, and operated by Reactor. And then it's already completed in end of 2019. And then it's the 25 years concession period by Keppel Infrastructure. So they run the plant, they sell the water to PUB. Right? So in terms of ensuring water sustainability, of course, at the end of the day, we need to ensure there are sufficient water supply. So I would call that as a hardware. Okay. Then eventually you still need the hardware, the human part aspect of it. So conservation and to value water, to enjoy water is a very important part of the whole equation. So you need the people of Singapore or people to cherish water and so that they don't waste water. Right? So in order to achieve that, of course, you need the 3P approach. Okay. So one is you facilitate, you mandatory to cut down excessive flow and wastage of water. And a certain important aspect is the pricing. Okay. So in Singapore, in terms of mandatory, so there is a requirement for how the tap and the washing machine, okay, how much water you can use. So and then there's this water efficient labeling scheme. So all electronic utensils that, or even taps and sink or shower head related to water have this water efficient labeling. So a 4-tick is the most efficient. So this gives a consumer a choice, right? Because usually consumer want something that will save their water bill, right? So so basically 17 reservoir, okay, in Singapore, all right, and there's this Active Beautiful Clean Water program to convert all these concrete canal into beautiful kind of waterways so that people appreciate and enjoy the nice environment. Okay. Now, in terms of consumption, as I mentioned earlier, Singapore is trying to reduce and encourage water consumption reduction. So in 2017, it's 143 liter per person per day of water consumption. So right now it's hovering around these numbers, okay? And in terms of water price, okay, I mentioned, right? In Singapore, what is the cost of water price, okay? So you find that since 2019, this is the latest price, okay? So basically you pay, there is a total of, there's a few categories, okay? First is that the pricing is based on the consumption, all right, per month. If you spend more than 40 meter cube per household per month, you pay higher rate. Okay, so this is a water tariff price. Either $1.21 Sing dollar or $1.52 Sing dollar. Then there's this water conservation tax. Okay, so you pay tax on the water consumption. All right. So basically 50% of the tax, okay, of the water price. Now then there's this water bond fee. So this water bond fee means it's the cost to treat your wastewater. You consume the water, the wastewater generated, then we pay for the wastewater treatment. So in Singapore, if you consume less than 40 meter cube per month, per meter cube you pay $2.74, $2.74 Singapore dollar. If you consume higher, more than 40 meter cube, the excess amount will be $3.69 per cubic meter. So is this considered high? I would say it is high in Asia, okay. But of course, Europe, US, I haven't checked the price. So, but at this price is considered pretty high in Asia, okay, certainly. So by having such a high cost, it hurts the pocket if you waste water. So for Singaporean, including myself, we are very careful. Like sometimes you forgot to off the tap, you know, kids forgot to off, after the kid will get big scolding, you know, because more money is going down the drain, right? Okay. So water pricing is a very important aspect. So, but of course, water pricing is also a very sensitive topic politically. So if you look at other countries, including, for example, Taiwan, okay, Taiwan water price is very cheap. 1 meter cube is only like $1. Okay, 1 meter cube is $1 Sing. So that is very low. Then of course, when you talk to friends in Taiwan, they say the politicians refuse to increase water price because you increase the water price, people not happy. You will lose your election. Right? So politicians are reluctant to increase water price. So the water treatment plant is having a big challenge because the price is so low. All right, so they have to find very cost-effective means of water treatment. Right. So if you look at new water, the price is cheaper. All right, so this is pricing for new water. It's only $2.33. So which is lower than $3.69. So this will encourage industry to switch over to new water because the price is lower. Now then there's this thing called industrial water in Singapore. Okay, there's this industrial water in Singapore. So what is this industrial water? Industrial water is basically an MBR permit water. MBR permit water. So this is the lower cost at $1.58. So industrial water is being used by certain industry, like for example, shipyard or this thing, when they wash a ship hull, the body or whatever, they no need to have very pure tap water. So they can switch to industrial water for cleaning purposes. Okay. So that in Singapore, there are 3 types of water. One is tap water, one is new water, and the third is industrial water. All right, so moving forward to the future, like I mentioned, Singapore has to increase its water supply by at least 1 time of today. All right, so how do we achieve that? All right, so of course, building more desal plant is the future, but at the same time, you need to reduce production costs, improve quality and security. Okay, so what are the solutions? So R&D look at biomimetic desalination, low energy desalination, in terms of cryptosporidium detection to safeguard drinking water, fish monitoring system to make sure the water are safe. So I think for those of us who are very familiar with water treatment, if you go to a water treatment plant, you'll find that at the last part of the treatment, before the water go out to your water storage, there's always a fish tank, right? Fish tank where inside there's fish swimming. So you'll be wondering, what is this fish for? So basically, they use the fish as an indicator of problem with the product produced drinking water. If there's toxic compound inside, the fish will die. So if you see fish dying, you know water has a problem. So you are using fish as a monitoring of your drinking water safety. Okay. So what people nowadays do is that in Singapore, there was a startup company came out with this imaging, you see. Because let's say you look at the fish. If you wait until the fish die, it means that the toxicity effect has been tremendously high. The fish was toxic. The toxic is so high that the fish died. But can you leverage on technology instead of waiting for the fish to die? Right? So there's this startup company actually capture the video, the image of the video of the fish swimming, okay, of the fish swimming. If the fish is under stress, you find that their swimming pattern will change, right? So you, based on the fish motion, it is a very powerful indicator way ahead before the fish die that something is wrong with the water, because the fish is under stress. The way they swim, you can see that it is not normal. So this is how we can leverage on technology to enhance our monitoring and also treatment process. And then, of course, one issue, remember that in Singapore, our wastewater is our source of new water, right? So how do we ensure that there is no toxic compound or illegal discharge into the wastewater? So there's this environment sense startup company where they develop electrochemical sensor, bioelectrochemical sensor that detect all these wastewater effluent discharge to detect whether there is a toxic compound. If there's toxic compound detected, you will trigger the auto sampler to collect the sample. Then you can then take this sample, go for ICP analysis for heavy metal to confirm and check what is the compound that is found in the illegal discharge or accidental discharge. So this system was implemented in Singapore since about 2 years ago. So right now in Singapore, there's 175 units installed around in Singapore, mainly detecting trade effluent from factory that uses heavy metals like electroplating. And they, over 2 years, they capture about 30 over samples of discharge exceeding the limit. And then they were subjected to legal prosecution. So this is another way you leverage on technology to safeguard your source of drinking water. And why is it so important? Because in Singapore, as I mentioned, the main treatment process is a biological treatment process, deactivated stuff. There was incident in the past where somebody illegally discharged copper compound. The wastewater entering the treatment plant was blue in color. The whole wastewater treatment plant biological system was down. Okay, so there was this incident. And if that happened, what happened? You will find that if your wastewater treatment plant can't work, you cannot treat your wastewater properly, your new water production will be impacted. You can't produce new water. So this is water security issues. Okay, so certainly growing the water industry, that's why Singapore invested substantial amount to grow the water industry, both through R&D companies. Right? So in Singapore, there are over 200 companies and more than 25 research centers. Okay, so with this, I thank you for your attention, and this is the part 1 of the lecture. Let's see whether you have any questions from the students and audience.
Okay, thank you, Professor Ong. Very insightful, and we also amazing about this DTSS. Okay, I will invite my student. If you want to ask or want to make sure whether Singapore citizen drink from recycled water or or something like that. If you have any question, please raise your hand.
Okay, so one interesting question. I think when I visited Turkey, that was in 2019, before the pandemic, 2020. So in Turkey, I was one of these friends. I was asking them. They also considering implementing new water, means the wastewater go through reverse osmosis and then UV, or they could probably put in oxidation process. So one of the questions I asked them, because in Turkey is a Muslim country. So one question I asked you, would you consider new water as halal? Because it's very sensitive, especially for Muslim, right? So his answer is that they already went through that process. They have this body, right? I'm not very familiar, but I think Prof. Awaluddin Numianto must be very familiar. In order to certify certain product as halal, there is a committee, right, that go through the review. So the answer that he told me is that the committee went through the review because of the treatment process, okay, because of the high quality purification process. The product water passed through and certified. It can be certified as halal. Okay, so this is a very important aspect, because especially if we're moving forward, there will be more water reuse. So from the Muslim angle, how do we consider, can we make sure it is classified as halal, suitable for consumption? So this has been, there's a precedent by Turkey. Okay, so of course, I'll be happy if anyone interested to know more, I can link up with my friend to know the whole process. Yeah. Thank you.
Okay, thank you, Professor Ang. There is other question from my student, that from Mas Bondan Al-Farabi. He want to know, whether is it possible or not to apply such kind of complicated technology and high cost infrastructure in like developing country like Indonesia, or we should stick on the other strategy, or what do you want to tell me about that, Professor?
Okay. The answer is this. I would say you only go through water reuse when you have a shortage of water, okay? Because new water is costly, all right? So if you have a source of fresh water from the river, from the groundwater, certainly I would say that is the best source, right? But if you have a water shortage, you only got two options. One is desalination or water reuse, right? So I always say that you don't do this because these are costly. But if you have shortage of water, then that is one of the solutions. So if you ask me, in Indonesia, are there places where you can implement this? Certainly, because for example, in industry, all right. So I know that in certain area where they have a shortage of water, they have no choice. They go desalination. The industry had to build desalination plant, all right, because there's not enough fresh water. So can they do water reuse? Certainly, all right. Then if you have water reuse, the cost will be lower than seawater desalination. But like what I say, you want to practice this water reuse, there must be a source of fresh water. If you are in the desert, there's no fresh water. What are you talking about? There's no water reuse to talk about. All right. So in my opinion, it really depends on case by case and where you are. Okay.
Oh, okay. So it's depend on the situation, right?
Yeah, right.
Yeah, right. But the interesting is because maybe my student is came from the other island also. That island is have a lot of water resources, but since they have a lot of water resources, so they use it a lot and they didn't care about saving the water. So it's kind of like a funny something like that. Yeah.
I see.
Okay. So, okay, see, we still have 5 minutes left before we have a break. If you have any question, please, you can type it or you can ask in Bahasa. I will help to translate. Or maybe Professor Ang can speak in Melayu.
No.
Okay? No? Okay.
No, unfortunately.
Okay. Unfortunately. Okay. Okay. Ada pertanyaan, silakan. Ya. So, Professor Ang, maybe how about the COVID-19, Professor? Because currently I read some literature that wastewater can be used as an early warning system
Yeah.
in COVID-19 detection. So, what is about the Singapore citizen perception about that when the government use like water recycling process in the new water? Thank you.
Okay, so this is an interesting question. So in Singapore, wastewater as a surveillance tool for COVID, we have done it. Okay, the NEA has done that, especially for the worker dormitory. Okay, then in NUS, I also helped to implement. Okay, I was part of the whole team to install auto sampler to collect sample and then analyze sample for COVID-19. Okay, but interestingly, if in front of new water, I think until today there is no issue being raised by the public, and the reason is because for the new water production, we have membrane processes, we have UV disinfection, all these things. So until today, very interesting. You raised a very interesting question. That in fact there was no concern. Nobody asked this issue about safety of new water. Okay, so of course, if you ask me from from a professional angle, in fact, the wastewater inside got all kind of bacteria, all kind of viruses. Not only COVID, there is polio. I mean, if you got polio, right, there will be all kind of viruses. Okay, then even HIV viruses, all kind of viruses. It has been there. It has been there all the time, right? But I think our treatment system has been robust. We got disinfection, all these things. So I haven't. We know that it works. We haven't heard any community or any pandemic, endemic due to wastewater, right? Okay. Yeah.
Okay, thank you, Professor. Okay, is there any question? Yeah, about this very interesting strategy to cope with the water scarcity in Singapore. Yeah, please raise your hand if you want to ask directly to Professor Ang. Okay, there is another question. Okay, so this is the question is from my student. He want to ask whether how to yeah, is there any solution for water supply in kind of rocky areas, because in their area is very rocky and it's how to say a lot of hardness in their water. So is it maybe using membrane is appropriate, or because the place is very high mountain and also the contour is very high, so maybe he consider about the energy or kind of a treatment process that's suitable for this area, Professor.
Okay, so if you ask me if those kind of places where hardness is very high, so if you, of course, you can use nanofiltration membrane because there have been technology NF or hardness remover. Okay, but if you look at all these areas, when you talk about membrane, it comes at the energy cost. There must be energy supply. So if you have water that is hardness very high, is it possible to have traditional hardness removal? Okay, so that's another option. But of course, you will say supply of this chemical, is it an issue, right? Because all this area may not be so easily accessible. I know that in certain area, it is very remote area. Okay, so if you ask me, maybe I also depend on the community size, right? So, but I personally think that a very effective way is rainwater harvesting. Okay, rainwater harvesting. How can you harvest the water, collect it, and then use it as a source of supply? So I will personally feel that that could be a better and more cost-effective way. Once you touch on membrane process, it's going to be costly, both in terms of energy and also maintenance. Right. So is there a cheaper way easier, more effective way. So these are things that we need to consider on a case-by-case basis.
So, okay, the answer is we can use another alternative source like rainwater. So maybe currently Indonesian people didn't harvest the rain, Professor. But in the ancient time, yeah, in our previous generation, they always have like a bucket in front of their house to store the rainwater. Yeah.
Yeah.
Okay.
Right.
So, okay, Professor, we will have a break for 15 minutes, and we will continue again in in here is 14. Yeah, so we will continue after 15 minutes. Please take your time.
Okay, see you shortly.
Okay,
Yeah.
see you. Oke, jadi bagi para ini ya peserta kelas, kalau ada pertanyaan silahkan bisa ditanyakan ya lewat chat box atau lewat raise hand. Ya, silahkan istirahat 15 menit. Kita ketemu lagi nanti bisa gabung lagi dan tetap on cam ya. Terima kasih atas partisipasinya. Okay, everyone, we will start the second session of this lecture. Okay, so for the second lecture, second session, Professor Ng will talk about the membrane bioreactor for wastewater treatment, and later he will talk about the some advanced process for recovery of energy from wastewater and nutrient from wastewater. For your information, Professor Ong, in this class, it's in Indonesia it's called unit operasi or unit operation and process. So this lecture, this subject is in the fourth semester, and it's account for 4 credit. So from the beginning, our student study about physical process, and after that is physical process like sedimentation, screening, flotation, and after that is yeah, a little bit membrane, but for introductory for membrane process, and after that the chemical process like adsorption, ion exchange, aeration, and water softening, and then biological process, basic biological process using suspended growth, activated sludge, and attached growth like a trickling filter or biofilter. And this in Patrick's lecture, we want to know about the application of some advanced process. I think it's very good opportunity to hear from the expert, Professor Ng from Department of Civil and Environmental Engineering, National University of Singapore. Professor Ng, please welcome.
Yeah, can you hear me?
Okay, yeah.
Okay, so good afternoon, everybody. So in this part of the lecture, I will start off with the membrane bioreactor for wastewater treatment. So MBR is the short terms for the membrane bioreactors. So the first question, what is membrane bioreactors? Okay, if you talk about membrane bioreactor, there might be different definition for membrane bioreactor. There are cases where people talk about extraction membrane bioreactor or membrane bioreactor for the bubblers using a membrane as a diffuser. So these are different options, alternative, especially talk to the chemical engineering people. So for wastewater treatment, when we talk about membrane bioreactor, we normally refer to the using membrane as a solid liquid separation. So membrane bioreactor is the combination of suspended growth bioreactor and membrane separation process. All right. So I believe you all must have take classes in this course about activated sludge process, right? So this is the conventional activated sludge process, whereby there's an aeration. We're talking about aerobic treatment, right? So aeration where oxygen is being supplied, and inside the aeration tank, there's a lot of bacteria. So bacteria combine with oxygen, and they convert organics into CO2. And the byproduct is more bacteria being grown, right? So with that, you go through a secondary sedimentation where you achieve solid liquid separation by gravity, and you produce an effluent that is low in suspended solids or bacteria. But of course, you cannot get zero. You still get a few ppm, at least a few ppm of TSS, right? And those are usually the bacteria. And then after the sedimentation, you will recycle the bacteria to the aeration tank. Then there's this excess sludge because of the excess growth, the net growth of the bacteria, you will take it out as a waste sludge. All right. So this is the conventional activated sludge process. Now, if you talk about, then this is a picture of a typical activated sludge process. And you can see that there's this aerator, which is having a propeller splashing the water as a mean of having oxygen transfer into the wastewater. Okay, so this is the aerator for aeration. And then you have this secondary clarifier, which is typical of the conventional activated sludge process. Now, of course, this is a picture of the raw sewage, activated sludge, and then treated wastewater. This is the typical activated sludge process. Now, so is there anything wrong with activated sludge process? I would say there is nothing wrong. Okay. So, but if we compare to what are the major challenges of activated sludge process? So first is large footprint. So first of all is that I'm not saying that activated sludge process is the only way of a good treatment process. Of course, if you talk about rural area, you've got oxidation pond, you've got wetland. Okay, so there are different type of systems that is suitable for different type of community and wastewater flow. But if you talk about activated sludge process, we are talking about when you are especially in a very organized city, big city where there is a huge volume of wastewater, you don't have a lot of land, you can't afford to have all these oxidation pond in for example, in Jakarta, that is too challenging, right? So in big city where the population intensity is very high, so we are talking about having a very high rate, high efficiency, low footprint wastewater treatment system. So classical is activated sludge process. So when you talk about activated sludge process compared to, let's say, membrane bioreactor, of course, activated sludge process will require a larger footprint. But of course, you ask me oxidation pond, it will be even larger footprint. Right? So 2 or 3 stages process is very typical. Even your MBR still need 2 or 3 stage process depending on treatment objectives. Now, but one of the key challenges is the settling problem of activated sludge. We hear about this thing called bulking, okay, foaming, all right, bulking, foaming. That is when you got the filamentous bacteria overgrow, and then these bacteria cannot settle. So normally, an activated sludge fail, okay, is when these bacteria fail to settle in the secondary sedimentation tank. Then you have all these waste bacteria lost in the effluent, and then you cannot have sufficient bacteria or microorganisms to cycle back to the aeration tank. Then your system will slowly fail because you're losing your bacteria. Okay. So having a very well settled bacteria or biological flux biomass is very crucial to the successful operation of these activated sludge process. So when you have bulking or foaming issue, then that is a sign of trouble for your treatment, the activated sludge process. So a surface of fine bubble aeration, certainly you need to have an efficient aeration system to have a high oxygen transfer efficiency. Then you can have high dissolved oxygen in order to reduce energy cost, obviously, right? Then if you, normally activated sludge process may need further polishing, such as disinfection or even filtration. It all depends on your target usage. But most of the wastewater treatment plant at least need the disinfection before you discharge to the receiving water body. Then you may have relatively dilute sludge generated. That's talking about activated sludge process. So if you study activated sludge process, typical biomass concentration or MLSS is about 3,000 plus, maximum 5,000. Seldom you go above 5,000, right? More than 5,000 is means your oxygen transfer, sludge settling may be a problem. Okay, so normally activated sludge process will maintain the MLSS concentration less than 5,000, right? Okay, so in a sense it is diluted compared to NBR. Okay, because NBR can go up to 13 grams per liter of biomass concentration. 13, so it's 13,000 even per liter of MLSS. Okay, so equalization of hydraulic organic loading required. It depends. If it's industrial, then certainly you need that. Otherwise, in domestic, normally is you don't need equalization. Okay, so this is the conventional activated sludge process, right? You have a bioreactor, you have a settler, you have a recycling stream, that's a sludge. So, of course, key control parameter include F to M ratio, food to microorganism ratio. There's always a range that you should maintain. Otherwise, you may have food starvation or overloading. If your F to M ratio is too low, you may have sludge spouting issue. Right? And then, of course, you can compute your sludge age. Right? So typically for conventional activated sludge, your maximum activated sludge age is like what? 10 days, 12 days is considered pretty high. Okay, that's typical one. But for MBR, you can go up to 15, 20 days of sludge age. Okay, so end of the day, is large sludge age a beneficial? Large sludge age depending on, of course, if you do biological calculation process, you find that if you have large solid retention time, sludge age or long sludge age, your bacterial concentration MLSS will be very high. Then your bacteria are more in the not in the exponential growth stage, which is more in the endocrine. It's more in the respiration. The growth rate is much lower. Okay, so there's always pro and cons. So there, if you want, some plant can run at the low sludge age, like for example in Singapore, activated sludge is run at 5 days SRT. Okay, because then Singapore temperature is high, so we never worry about nitrification, denitrification rate. So the sludge age is only 5 days, so your MLSS concentration will be not so high. But the purpose is, objective is basically to enhance the oxygen transfer, because if your sludge is higher concentration, your viscosity will be higher, and then your oxygen transfer efficiency may not be as good compared to a more dilute sludge. So depend on your objectives of your treatment system. If you want to have more biomass growth, then your sludge age should be lower. Okay. So basically, so there is a constraint in terms of the sludge MLSS. So you should not be more than 6 grams. Otherwise, your settling efficiency is a constraint. Okay. So if you look at activated sludge process, why you cannot have too high solid retention? Because your MLSS will be too high. If it's too high, your settler cannot settle well. The sludge cannot settle well. Then you will have a problem in terms of effluent quality and also losing biomass. So because of that constraint, you cannot have very high biomass concentration. But for MBR, you will have a lot of flexibility, because you no longer require the sludge to settle well in order to achieve good bacteria and water separation. Okay, so MBR give you a lot of flexibility in terms of solid retention time, whether you can run it very high MLSS, long solid retention sludge age, or solid retention time, or you can run it at very low solid retention. So that gives you the flexibility because of the settling issue of the biomass. Okay, so in membrane bioreactor, basically I would say it's more or less an activated sludge process. Oxygen supply in the aeration tank, either as air or pure oxygen, and most of the time is air. Okay, so it's the biological part is very similar to the activated sludge process. So microbes will form microbial floc, or we call it biofloc. Okay, and then organic content will be reduced, convert to CO2, and then separation of microbes, floc, and solids are done by membrane. So that is the difference. Okay. Now, if you ask me, what is the MBR characteristic? So basically, I mentioned earlier, we replace secondary clarified by MF or UF to achieve more reliable solid water separation activated sludge. Because of that, because if you have a activated sludge process, right, usually the discharge quality is controlled by, of course, you have a SS, you have a BOD or COD. Right? Now, if your settler don't work well, you've got more solid coming out. When you do a BOD test or COD test, the value will be higher because your biomass contribute to organics. And then you may exceed your discharge standards. So settling is very crucial. Now, if you have a membrane to replace the settler, the membrane, no matter how it runs, it will retain all your bacteria. So you will only produce a permeate or effluent that is suspended solids free. So you only have a dissolved organic. So you will be able to ensure a reliable water quality that always meet the discharge standard, unless your bacteria died or your bacteria is not working. All right. Okay, so you can produce an effluent of much higher quality than the conventional activated sludge process. All right. High rate of removal of particulate matter with effluent probably below or in the range of 0.1 or 0.2 mg. So you find that the water coming out is not like crystal clear. You don't see any particles or solid. Okay. So it's implemented for stringent discharge standard. Water we use or for direct use as a feed to our membrane unit without additional filtration or MF or UF. Like I mentioned in the part 1, if you put an MBR, you already use an MF or UF as a pre-treatment, as a separation. The permeate coming out is suspended solids free. You can take this product water to go into reverse osmosis directly for RO treatment without any additional MF or UF. Now, some places also implemented MBR because of the stringent discharge standard. And then they want to do water reuse. So for example, the most famous one is the Beijing Olympic, right? There's this Olympic, there's a treatment plant. Basically use an MBR, produce the permeate water, and this permeate water is being used for the irrigation, golf course irrigation, for aesthetic water fountain, all these things. Okay, so that is where your MBR can be considered for these purposes. Now, one of the constraints that it always requires fine screening of the influent stream, range 1 to 3 mm, to protect membrane from abrasive and stingy wastewater component, as hair in particular. So you find that the MBR, because of the nature of the system, especially polymeric, okay, because UFMF membrane, most common one is polymeric, means it's organic based, polymer based. So they can be cut by glass pieces, glass fragment, and then the hair can cause clogging of the membrane, especially at the potting area. So usually you need to be removed. That's why you need a fine screening, which range from 1 to 3 mm. Now, of course, the other membrane commonly used ceramic. I can talk about it later. So if you talk about ceramic membrane, then the durability is higher than polymer. You are less concerned about glass pieces that cut your membrane, because ceramic is much more stronger and durable compared to the polymeric membrane. Okay. But nevertheless, MBR or UF screening usually need a fine screening before that. Okay. Now, so MBR, because you have a MF or microfiltration or ultrafiltration UF, it provide an absolute barrier to suspend solid, a lot of very high solid concentration. Means you can maintain a very high biomass concentration or MLSS, MLVSS compared to the activated sludge process. Okay. So like I mentioned earlier on, activated sludge should be less than 6 grams per liter. But MBR can range from 8 grams to 20 grams per liter. Okay. But if you ask me, most MBR should not run more than 13 grams. Maximum is 13 grams per liter or so. The reason is because if you go too high, the membrane fouling can be a challenge. Okay. So for MBR, you're not relying on activated susceptibility to retain to retain activated sludge in the biological process. So you can run the SRT or sludge age of 10 to 40 days or longer. Okay, but typically it's about but activated sludge is usually less than 10 days or maximum 12 days. Right? The MBR can go up to 20 easily, or even people run longer. But if you ask me, of course, you don't go too high because MLSS is too high. Then your membrane potentially can be fouled much more rapidly. Okay. So with correct process design, MBR can produce similar or better effluent quality than the activated sludge, including VOD, nitrogen denitrification, and biological phosphorus removal. Okay. In most cases, MBR system will produce effluent, okay, similar quality as a tertiary effluent after membrane filtration. Okay. And operation at much higher concentration of activated sludge than the CASB conventional activated sludge process resulted in more uniform nitrogen denitrification and more robust and stable biology. And in most cases, MBR process will be less affected by operation upsets and presence of toxic constituent in the inflow. The reason because you have such high biomass concentration in the aeration tank. So if you compare the quality, okay, conventional activated sludge, VOD, 5 to 7 ppm, milligram per liter. MBR typically less than 0.4. TSS less than 0.4. WT less than 0.2. But activated sludge 2 to 5. Ammonia less than 0.5. Total nitrogen less than 5. TP less than 0.2. So MBR normally will produce a much better effluent quality compared to the activated sludge process. So typically, secondary disinfect barrier is required when MBR effluent is shut, reused, or recycled. Okay, so you can disinfect by chlorine, by UV or ozone, okay, as a secondary barrier for pathogen. Because MBR can remove particles, but it cannot guarantee you absolute virus removal. Okay, so you still need a secondary barrier by disinfection. And also, you cannot guarantee you don't have a broken fiber in the MBR through long-term operation. So it is always advisable to have a secondary barrier of disinfection. Okay. So MBR process remove particles very efficiently from treated water, improving effectiveness of the subsequent disinfection process. Because you know, if you have UV, okay, if you got solids, certainly it's not as effective if you have a totally suspended solids free, right? Because we learn ultraviolet disinfection. You got particle, you got any virus hiding behind the particles. If they are not subjected to UV irradiation, then the efficiency of disinfectant will drop. All right. Disinfection demand of chlorine, inactivation intensity of UV and ozone is much lower for the MBR treated water than required for effluent from the activated sludge system. Okay. So it means that MBR can provide significant reduction of the size of disinfection or inactivation equipment, lower OPEX costs due to lower energy demand, and lower cost of chemical for disinfection or microorganism inactivation. All right. So if you look at the trend in the world in terms of full-scale MBR, over the last 10 to 20 years, we see there's a very big increase, okay? And China is the biggest in terms of treatment capacity, followed by US, okay, and Sweden, France, Korea, also at least that's on this chart, okay. So there's an increasing trend of MBR application, all right. And you ask me MBR, there are basically two configurations. One is the side stream MBR, where you got your aeration tank, then you use a pump to pump through a membrane module, and your recycled sludge will go back to your bioreactor. So under this kind of system, it's a pressurized system. Okay, you apply a pressure to push the water through the either the MF or UF membrane to produce a foam. Right? So this is a pressurized system for substream MBR. Now, the other commonly used system is submerged system. Basically, you submerge your membrane into the bioreactor, and then you provide a suction pressure to suck out the water through the membrane. So this, just imagine you're like having a straw, right? You suck. When you use a straw, you need to provide a suction, right? You use a suction force to suck out the water, right? So this is very similar to that concept. So now if you look at the bottom diagram here, you see that normally if your system is very small, like a very small treatment plant, then you can put a membrane into the bioreactor, so you have a single tank. But if you are a big wastewater treatment system, you find that your membrane tank requirement is much smaller. So you have your biological tank upstream, and then you have a membrane tank right at the last stage. Then you find that from a membrane tank, you need a recycle similar to the secondary clarifier. You need to recycle stream to bring the biomass from the membrane tank to the front of your activity tank. So this side stream I mentioned, every unit connect to a biological externally. Side stream setup allow easy expansion of existing wastewater treatment plant, certainly, because you can imagine that if you want to expand, you just add in more module, connect more pipes, right? But if submerged tank, you need to make sure you have a tank available for you to submerge the membrane. So if you talk about expansion of plant, of course, side stream will be much easier compared to submerged, right? The side stream hydraulic operation is by pumping. That's you need a pressure, positive pressure. So address fouling problem of side stream reactor need and increase pumping rate to achieve effective scouring and membrane surface at a steep cross velocity. So you look at this. So later I'll talk about membrane fouling. All these membrane systems, one of the major challenges is membrane fouling. So what is membrane fouling? Basically, membrane, the pore is blocked by fouling, and then your water cannot permeate through easily. Okay. So means that in your MBR operation, it is always crucial to minimize the rate of membrane fouling. All membrane will foul. It's a question of how fast you foul. Okay. Just like you wear a clothing, right? Your clothes will get dirty. The question is how quick you get dirty, right? Whether it's slow or you go and roll in the sand, roll in the mud, then you get dirty very fast, right? So all clothing need to wash. All membrane need to be cleaned chemically. The question is how frequent, how quick you have to clean your membrane. So in order to minimize scouring, membrane fouling, there's this thing called scouring, S-C-O-U-R-I-N-G, scouring. You want to create a sweeping force to sweep any foulant that is trying to attach to the membrane surface. So in the crossflow system, you have a high velocity crossflow. Remember, there's a pump, a positive pressure pump, right? Part of the water will force through the membrane. Part of them will be travel to the end and recycle that. So there's a crossflow velocity. So you need to pump at a high rate enough to generate a crossflow velocity strong enough to create a sweeping force. Okay. Now in the submerged system, all right, you can see that there's this bubbling. Okay. This bubbling is trying to create a two-phase, having the bubble to shake the membrane module, fiber, or provide a scouring effect that helps to decrease the rate of membrane fouling. Okay, so that is a commonly utilized strategy. We'll talk about this more later. Okay, so coming back, a side stream reactor need an increased pumping rate to have a crossflow velocity high enough to provide effective scouring. So this is a crossflow MBR system. All right. Now, suspend MBR. So the module go directly into the reactor. Hydraulic operation in submerged MBR is by airlift. Okay. So you provide a vacuum pressure to create a permeate stream. Submerged MBR uses intensive force bubble aeration to agitate and scour the membrane. Okay, so you produce a bubble. Bubble will cause the membrane fiber to shake, to vibrate, and that try to shake off the foulant. And then you also have bubbles scouring the surface to produce intense recirculation and delay flow. Okay, so that is how the system, right? You submerge a membrane in, there's an air jet provided at the bottom, bubble will rise, and that provide the scouring effect to the membrane surface. So the question is, immerse or side stream MBR, which one is better? Based on a lot of report, internal submerged system or immersed system use less energy but operate at lower flux with more membrane surface area. So there's always a pro and cons. Internal means side stream users, or internal means submerged users bubbling or two-phase flow to control deposit layer. So there's always pro and cons to both systems. Okay. So this is an example of this Xenon external membrane and immersed system. So surface area, you see that the flux, okay, typically MBR is maximum 25 sustainable operation. So although I read 20 to 50, but in reality, the flux is 25 maximum for sustainable operation. When I say maximum, it means the normal operation, okay, 25 RMH. But side stream can go higher, okay, and then pressure 400 kPa. Then for immersed system, it will be negative pressure, 20 to 50 kPa, okay, up to 20 to 50 kPa. Velocity, 3 to 5 gross flow velocity, but immersed system don't require. But immersed system need an airflow rate, about 40 cubic meter per hour for a GW 500 module. So energy consumption 4 to 12 kilowatt hour per meter cube of product water for side stream versus 0.3 to 0.6 kilowatt hour per meter cube. So you can see that energy wise much lower for the submerged system. Now, so advantage of external membrane module. Aerating tank float your oil grease, easier to clean membrane chemical without upsetting biological process. Ability to control environment around the membrane module better, flexible operation, delta P may be changed to accommodate into inflow rate. So this is for external membrane modules, okay? So especially the last 2 points, right? For the third point, clean membrane chemically, okay? Without upsetting biological process, that is true if you have a single tank system. So normally what they do is that, like for example, in this case, you want to chemical clean this system, right? You just turn off, of course, in full scale system, there are many membrane module train. So you can shut off that train and then switch to cleaning mode. So for side stream, it's very easy. Now for submerged MBR, there are 2 types of cleaning. One is called in situ chemical cleaning versus chemical CIP, clean in place. So in situ cleaning is just backwash with hypochlorite, and then some of this hypochlorite will go into the mixed liquor. But because the amount that is backwash is very little, so the impact on your bacteria is minimum. Okay, that is called the in situ backwash, right? But if your membrane is so foul so badly that you need chemical soaking, then what they do is that they have to shut off the membrane tank, okay, drain out the bacteria or the mixed liquor, empty the tank, then fill in the chemical. So you can see that the chemical cleaning will be much more troublesome because you need to drain out the mixed liquor, you have to fill in the chemical. After the soaking, cleaning, you need to drain away the chemical and then flush with clean water and then fill up with the activated operation. So there's always pro and cons to those systems. Okay. Now, okay, so advantage of submerged membrane, less pumping cost and energy cost is lower. Membrane installed in the existing tank, you can always put it into the activated sludge tank. So for submerged membrane system, you can retrofit from the activated sludge process. Just shut off the secondary clarification, convert some of the final tank into a membrane tank. Okay, larger module can be designed for larger flow to be treated. So depend on the flow rate, you can design the membrane module. Okay, in terms of submerged membrane company, there are many companies right out in the market. So more well-established include Xenon, US main core, this is the earlier name, now it's called DuPont Evoqua, that is the main core, we brought over main core. And then you got Japanese Mitsubishi, okay. And then these are all the hollow fiber, okay, like spaghetti, all the spaghetti type. And then you got flat plate vertical like Kubota, okay, Toray. These are flat plate and frame system, okay. So this is like hollow fiber, okay. So you look at this, what are all these things? This is like the hollow fiber membrane. So basically, if you look at this fiber, it is just like your straw, okay. There's a hollow tube inside, right? But now the wall of your straw is polymer with micropore, right? 0.45 or 0.04 micrometer pore size holes, okay, that allow water to permeate through. And then at the bottom, there is a holder. On the top, there's a holder. And then you provide suction, then it will reduce the permeate, all right? So this is a Xenon G fiber. So we can see that hollow fiber with outside in means the dirty water is outside, and then your water will flow inwards. So that's why it's called outside in, all right? So for this, G width is 0.9 millimeter internal diameter, 1.9 mm outer diameter, means the thickness. The wall thickness is about 0.5 mm, okay? Chlorine resistant polymeric membrane usually is like PVDF material. Pore size in the ultrafiltration range 0.04 micrometer. Permit drawn by suction will permit air bubbling, induced turbulence to keep membrane clean. Okay. So in this case, you can see that outside in hollow fiber shellless module, open tank system, gentle suction, all right, air scouring, provide the air at the bottom, feed and purge at tank level. Okay, so these are the system. So membrane scouring. Okay, so you can see that our membrane system got two types of aeration. One is for the regular fine buffer for biological oxygen requirement. That is called the typical aeration or the diffuser aeration, right? That is for biological demand. Then they got this coarse bubbling. We call it scouring, okay? Of course, it's the most significant contribution to running cost of the MBR. And then the aeration if you increase by stacking the membrane and employing intermittent aeration. So right now, in order to reduce the aeration cost, many of these membrane suppliers don't require continuous bubbling. So they will have a protocol of aeration for a certain period, stop for a while, and then re-aerate. So it's called intermittent aeration. Also, probably single most important parameter determining grouting. So this scouring is crucial to delay membrane fouling. So this is when you have this scouring, there is basically two-phase scouring. You got the air and water, right? So basically, you inject air, and this bubble will rise, and then this bubble will scour and travel along the membrane surface, providing a scouring effect. Okay. So minimize solid concentration build up in modules, uniform distribution in the modules, reduce local solid concentration, result in energy saving. So normally you can see that as this aeration implementation, all these bubble will rise up, right? And then you bring along with you the permeate liquid, then you will form a circulation movement. Okay. And then this blue color is the permeate that travel inside the hollow fiber. So the role of the bubble provides surface shear, induce liquid motion, induce fiber movement. Okay, you basically shake the membrane. So I always like to use this classical example. Let's say your clothes is very dusty, right? Your clothing is dusty. How do you shake off the dust? You shake it, right? With the jet, right? Then your dust will come out, right? So for membrane is the same. How to create this jet or the shaking? Cause you create by injecting a big burst of bubble. So right now, what have been proven most effective is to create a sudden intermittent big burst of bubble that create the shocking and vigorous shaking of the fiber. So the current company like Evoqua, Genon, now Genon sold to Suez, okay, earlier was sold to GE, now it's Suez G-Reed membrane. They implement intermittent coarse bubble, a sudden release of coarse bubble to induce this vigorous sudden fiber movement. Okay, so this is an example of this bubbling. Okay, so this is how the membrane module, each module about 46.5 meters squared. Per cassette, you join them together, you form a cassette 270 square meter. So the overall height is about a human height length. Okay. So you can see that all this membrane will assemble into a cassette, a cartridge, and then you use a lift to lift it and then lower into the membrane tank. Okay. And then this is how it look like. Okay. Once you install into the system, on top you create a suction force, the permeate will come out, and then at the bottom is your waste solid that you do for the circulation or wasting. Okay. Then this is Mitsubishi my membrane fiber. This is earlier on the horizontal one. Now they also changed to vertical form. Okay. Mitsubishi is 0.45 is more of a microfiltration membrane. So filtration mode, suction pump on for 8 to 13 minutes, air blower on. Resting mode, okay, suction pump off for 2 minutes, air blower on, no back washing required. So this is the earlier continuous bubbling mode. Okay. Any mode perform when pressure increase by 0.2 bar. That is approximately every 2 to 3 months. Okay. So this is a flat sheet membrane module. Okay, polyester. This is an example. This is a coarser one, 50 micrometer. So the membrane got different type of pore size. You can have very coarse one, like this 15 square meter. And then Kubota is a coordinated polyethylene material. Okay, and sheet for a pillow with sponge inside. So you have this sponge inside to create a porous spacer. Okay, and then that is when you aerate it, right? Then flat sheet align vertically. Then you have a very good scouring effect. In this case, you find that your flat sheet membrane don't vibrate. Okay, not like the hollow fiber. When you scour it, right? When you scour the membrane will shake. Okay, but in a flat sheet system, the flat sheet is rigid, but we provide the air scouring to very effectively scour the surface. Okay, that is a Kubota system. So basically, your wastewater come in, all right, you permit, and then your treated water go out. Okay, so this is a very classical example of the MBR operation. This is how the membrane cartridge will sit inside the tank. Okay, and then pilot scale system. That is the membrane cartridge. All right, and then membrane casing. And then you got your diffuser at the bottom, and then your manifold with all the tubing connect to individual plate of membranes. This is a view of the flat sheet Kubota membrane in place inside the tank. All right, and then of course, during your replacement of the membrane, you can hook up each of these modules, and then eventually you need to the whole cartridge need to lift up and then lower into your tank system. And then this is how your top view of membrane system look like. Okay. So this is your inlet wastewater treatment tank, right? And then inflow coming in and then go through a membrane permeation. All right. This is a picture of a small scale system in a container system. All right. And you can see that this is your membrane tank with all the flat sheet Kubota membrane. And then this is a side stream MBR. You can see that these are all the, this is a pen air exflow membrane. This is an example of side stream filtration unit. Now, in terms of the membrane material, okay, and the pore size. So normally we classify as microfiltration or ultrafiltration. So microfiltration range from 0.1 to 1 micrometer versus ultrafiltration is 0.001 to 0.1. So anything less than 0.1, we call that ultrafiltration. Okay. So like the G rate is 0.04 micrometer. Okay. Then you find that your membrane got asymmetric pore structure typically used. And PES and PVDF are emerged as market leader. Now, how do you see that? What do you mean by asymmetric kind of membrane structure? So if you look under the SEM or okay, you will see that you look at the membrane, there is a porous skin, and the bottom layer is a porous structure, okay? And then top is a skin layer, 0.1 to 0.5 micrometer. Sub layer is 20 to 200 micrometer. So you can see that the active rejection is only the top skin layer, okay? And then you can see that it is asymmetric because the top layer and the other side is different, okay? Different in terms of the structure. That's why I call it asymmetric pore structure, all right? Now, you see that the polymer got different type. One is cellular acetate. Okay, this is the earlier day version. Cellular acetate is easy for fabrication, but cellular acetate is biodegradable. Okay, so it's susceptible to hydrolysis, and then it's not as good as chlorine tolerant. Okay, and chlorine resistant. So these are early days where people use cellular acetate as a membrane material. But in current days, people use PES or PVDF because PVDF best for flexibility used with air scouring, PS best for polymer blending and ultrafiltration rating. Okay, then PEPP, these are other materials susceptible to oxidation, limited blend capacity. So the diagram here you can see, okay, most of these membrane fibers, they are produced in mass production. Okay, it's different from the membranes used in the laboratory analysis. For example, if you buy 4.5 cm diameter filter disc, right? It's round in shape. You use it for doing suspended solids filtration, right? Then you got this filter can be made of fiberglass. You can heat it at 550. So you look under microscope, their hole is absolute pore size. It means each pore size is 0.45 micrometer or 0.2 micrometer. Every hole is of the same pore size. But in all these industrial scale polymeric membrane system, you find that they are asymmetric. Their production has to be very fast. So all of these are made during phase inversion using an intruder. So the polymer will extrude out and then immediately submerge into the water. And when it submerges into the water, it forms this structure. And then you find that the pore size is basically follow a normal distribution. So you look at this diagram here. Pore size distribution for commercial PES and PVD. So the darker dot is PES. So you can see that there are some pore size bigger, smaller, and then most of the pore size is around 20, about 25 nanometer. All right, and then this PVDA is about 35. Okay, so what does that mean? It means that there are still some pore size that is much bigger. Okay, that's why in all these membrane, the pore size is known as nominal pore size. Nominal, it's not absolute pore size. Nominal means most of the pore size is of that size. There are some pore size smaller, some pore size bigger. Right? So that is something unique, and it is and most of the big scale applications are normally asymmetric membrane with nominal pore size. Right? The production can be mass produced rapidly. Okay. Now, so in this bottom diagram, it shows the strength versus the elongation. So you can have PVDF at very high strength. PSPS also have very high strength. But in terms of elongation, the best is PVDF. Means it can have a good elasticity. It means that it's not easy to break. Okay, you can elongate. Okay, so means that under vibration mode, it is much more durable for PVDF. All right. So this is the MBR configuration. So this diagram show you the typical potential configuration. For A is a external pressure difference or side stream. So you got aeration tank, you pump to the membrane module, and then the retentate recycle back. All right, now then for B, C, and D, okay, these are the for B is called integrated submerged. So you have an aeration tank, and then the membrane is put at the end of the aeration tank. Okay, part B is you have an external membrane tank, all right, and then retentate recycle back. Even for B, you still need to have a recycle back in front, okay, because otherwise all your biomass flow towards the end of the tank. So you still need a recycle tank to go to the front. And then part D is a vibrating, rotating membrane system, all right. So these are the possible different configurations. Now, in terms of the MBR for wastewater treatment, you can see that usually you still need the grid removal chamber. Equalization tank is really optional. Usually for domestic wastewater, you don't have optional. Usually you still have a primary sedimentation tank, fine screen MBR, then disinfection. All right. So this will be the very typical of an MBR. Usually primary sedimentation is required, especially you are talking about domestic wastewater, because there are still quite substantial amount of solids. Now, how does the membrane influence, what kind of factor cause this membrane performance? Like I mentioned, the bubbling two-phase is crucial, intermittent backwash. The module design to minimize whether it's a hollow fiber, potting, flat sheet system will impact on your fouling. And then fouling model, whether it's a particle, solid, critical flux concept, and then you optimize your performance and process control, all right? So what is membrane fouling? Membrane fouling means your foulant attached on the membrane surface, okay? So normally in a wastewater treatment system, you will need to run at a constant capacity because you cannot say, hey, my treatment capacity dropped, you know? Otherwise, what my wastewater keep coming, I need to treat, right? You don't have a holding tank for it, especially for domestic wastewater. So your capacity is maintained constant. So what happens is that TMP, okay, as your membrane filtration time increase, in order your membrane will foul. When your membrane foul, in order to have the same capacity of permeate flow rate, I need to create a more negative pressure. I need to increase the pressure, suction pressure, in order to pull out more water. So just imagine, okay, we some of us, sometimes we drink bubble tea, right? Bubble tea. Then you find that, hey, this bubble tea bubble stuck in the straw, right? Then how do you suck? You put to suck stronger, right? In order for the water to flow. So it's the same. For a membrane system, is like that. Similar. When your membrane surface gets foul, in order to pull same amount of water coming out, I need to have a stronger suction pressure. So the TMP is an indicator. This is called transmembrane pressure to produce the same amount of water flow. So usually run at low TMP, slowly you will increase. So this is called the stage 1 slow and gradual increase in TMP. Then stage 2, there will be a sudden increase in order to produce the same amount of water, same amount of flow rate, product water flow rate. So this is a sudden increase. So when you hit a sudden increase until a certain cutoff point, for example, 40 kilopascal or 50 kilopascal, then they say too high, you must stop your membrane system for cleaning. Okay, so this is called membrane fouling. All right. So this is example of a foul by the biomass. Very thick layers stick on the membrane surface that block the water flowing. Similarly, and then what are the factors influencing? So of course, wastewater property, the type of organics compound will affect, and then your configuration, okay, and then membrane property, the operating condition, and the sludge characteristic, whether the bacteria is very sticky, all these things will impact on the fouling rate. Okay. So how do you control? Of course, it's the flux, or how high is flux. When you flux means how many, usually it's called LMH. The amount of liter of water produced per meter square of membrane per hour. That's called LMH. Okay. So you want the membrane to foul the lowest. Don't run at too high flux. Run at 10 LMH. But running at 10 LMH means that you need more membrane area to achieve the same capacity. So that's why MBR maximum 25. If you run 35, the membrane will foul very fast. then you got problem because you need to stop the system to clean the membrane. Okay. That's one way. Next is to increase turbulence, increase crossflow in side stream, increase emission. Okay, that is during the operation. But then you can also have physical cleaning or chemical cleaning. That's when you foul very badly. Or you try to operate such that you improve the sludge characteristic, make sure the sludge is not so sticky. Okay, so all of these have cost implications. All right. Now, this is an example of the different way people look at chemical membrane cleaning. Okay, so membrane foul, you try to run at low subcritical flux condition. So what is called critical flux? Critical flux concept means that the flux whereby you run above that, your membrane foul very fast. That's called critical flux. Okay, so you try to run your system below your critical flux. Okay, so membrane will foul. There's a reversible or irreversible fouling. So if it is physically, you try to clean it by membrane fouling. Okay, and then possibly by biological cleaning, then that is something else we will talk about it. Okay, and then this biological cleaning including this thing called quarrel quenching. Okay, it means cell-to-cell communication, so that you can delay membrane fouling. All right. So the classical way is still very much by physical scouring. So on the right figure, you can see one way to achieve less fouling rate is intermittent filtration. People try ultrasonic particle scouring by adding like PAC, powder activated carbon, or even vibrating membrane. Okay, then that is two different configuration. Then you can achieve by backwash, by chemical enhanced backwash, or clean in place. Okay, all different methods. Okay, or intensive chemical cleaning. Okay, so these are all approach that try to minimize fouling rate and also for membrane cleaning. So how can we control? Okay, so these are the whole membrane system. All right, so what's your rate coming out? Your flux will impact on membrane fouling. Bioreactor, how to make the cell less sticky in the nature that is more attached to the membrane surface slower. All right, and then air scoring. So these are different way. So maybe I'm going to escape this one. So critical flux. Okay, so critical flux means the flux whereby if you run at the flux higher than the critical flux, then the foulant attacks very fast. So this is below critical flux, then the particle or solute, your foulant will not attach to the membrane surface so fast. All right, so that's the critical flux concept. All right. So critical flux is increased as bubbling increase. Okay. So then if your bubble increase, your critical flux will increase. So to reduce fouling, you operate at the flux lesser than the critical flux. So lower flux means you got capital penalty or high flux energy penalty. So it's pro and con. If you, like I say, you run at low flux, you need more membrane area. So your capital cost will be high. If you run at higher flux, your membrane will foul faster. Your energy usage will be higher because you need to run at high TMP, right? And then more frequent cleaning. So operation cost will improve. So it is a true and okay. So similarity and differences with activated sludge. Okay, biological kinetic very similar. Slightly different in the sense that because you run your system at very high solid retention time, your bacteria is more in the endocrine, endogenous respiration stage. Yeah. So their growth rate is lower. Okay. And the differences is the efficiency of removal, footprint will be lower, effluent quality better. Okay. So treated effluent particle free, compact process with smaller footprint, odor containment, you can control it. Processing advantages, micro not selected for frog formation, means any frog, because your bacterial membrane can remove very well. But of course, if you got bulking forming bacteria in the MBR, it still can produce good effluent quality, but the only issue that the membrane will foul faster. Okay, collar and micromolar can be retained for improved bioactivation. Okay. Other benefit, eliminate the problem associated with bulking sludge, allow increased biomass concentration, increased loading rate, and promoting higher reaction rate, increase in temperature and intracellular enzyme, kinetic extent. Disadvantages: fouling is an issue. Energy usage may be higher than conventional because of aeration, scouring. Occasionally, chemical cleaning required across the membrane. Small to moderate scale operation has been established. There are large plants, okay? Nowadays, you got many large plants, okay? Sludge produced tend to be more difficult to dewater, okay, because your sludge is older, all right? Disseminate prone to blockage, valve fouling, scaling. Blockage are caused by hair fiber blocking the membrane inlet. Valve fouling is caused by residual biodegrade organic substances. Scaling due to inorganic substances can happen if your calcium magnesium too high. High cost of membrane replacement. Hollow fiber used in M2 breaks if it is hollow fiber and only repaired after time-consuming inspection. Okay, so these are So these are some operating protocol. I think I won't go through that. All right, and then cleaning. You can use sodium hypochlorite. Sometimes you use citric acid. Sodium hypochlorite is the most common, and sometimes they also use oxalic acid for chemical cleaning. Now, in kind of biological removal. So, okay, I just going to cover a little bit. So, first is the ammonia nitrogen removal. So, most of the time, wastewater is in the ammonia form. So, nitrifier will convert to nitrate, and then the nitrification under N2, okay, to convert to nitrogen gas. All right. So, nitrification will occur simultaneously in the aeration tank because you have present oxygen, and there's always nitrobacter, nitrosomonas present. You convert to nitrate. Okay. So, but nitrate grow very slow, therefore sludge age should be maintained greater than 3.5 days. So once you operate your solid retention time 5 days and above, 3.5 days and above, you will have nitrifier. So nitrification is usually not a problem. Okay. So this is typically of a nitrogen removal process. You have your aerobic. Okay, wastewater come in. Anoxic is where you do not have high DO. You put a probe into the anoxic tank, the DO is 0. Okay, there's no oxygen. So in the anoxic tank, nothing will happen to the ammonia. All right. Then this ammonia go to aerobic in the presence of nitrifier oxygen. Ammonia will convert to nitrate. Okay. Organic will convert to CO2. Then you have a recycle stream that bring the supernatant, the mixed liquor back to the anoxic tank. This stream will be high in nitrate, okay, and some oxygen. So when you come to anoxic, organic is present. Bacteria, the nitrifier will take the nitrate and the organic to convert to nitrite and then go to N2. So your anoxic will achieve the nitrification. That's how the system. So your permeate coming out will have maybe around 5 to 6 milligram per liter of nitrate. Ammonia almost 0. So in order to enhance nitrogen removal, you can have multiple stages like anoxic aerobic, anoxic aerobic, anoxic aerobic, and finally the membrane tank. So you have a multiple step of anoxic and aerobic combination. Then you can reduce the nitrate concentration in the final tank. So this is how the nitrate removal is being achieved. So this is in the MBR, we have an anoxic tank, aerobic tank, then finally a membrane tank. Okay, so this is how nitrogen removal is achieved. And this is how the full-scale plant can look like. Anoxic tank, aerobic, over membrane tank. And then you have internal recycle, or you can recycle because your membrane tank usually have very high DO. So they bring this high DO to the front of the aerobic zone. Then for after the DO have reduced, then they take this stream, low in DO, go to the anoxic zone. So that is how the nitrification is achieved effectively. So this is in Singapore, there is Ulupana MBR demonstration plant. You've got anoxic aeration tank, followed by membrane tank. Okay. Then the fine screen is after the aeration tank. All right. So you can see that this is your flow about 23,000 meter cube per day. Influent BOD about 138, COD about 292. Total Calder nitrogen 48, ammonia about 32. Okay. And this is the xenon hollow fiber. All right. And then operation condition, sludge 8, 10 days, HRT 6 hours. Okay. And then the final effluent quality, the product water quality, you can see the turbidity is 0.02 NT, ammonia 0.2, TOC 4.8. All right. Nitrate 6.3. Total P 3.3. So it's a very good quality water. suitable for new water production. In terms of energy cost, the power consumption is about 0.55 kilowatt hour per meter. This is with continuous aeration. Right now, with intermittent, you can go down to 0.3 kilowatt hour per meter cube. And you can see that membrane air scouring is the majority of the energy consumption. All right, and then this is the power consumption. Okay, you can see that about 0.55 up and down. All right. So water reclamation process train. So you can see that this is a conventional. Now with MF pre-treatment, MF UFRO, then finally you put the MBR, you can simplify your treatment train. Okay, that's how the system looks like. Okay, advances, of course, there are a lot of R&D looking at the impact of operating condition and SRT impact. So running at different retention time, 3 days, 5 days, 10 days, 20 days. So you can see the MLSS increase from 4.5 to 22 grams per liter. But surprisingly, you find that 3-day SRT fall the faster because of the extra polymeric substances, the organic that is very sticky. Okay, and then looking at the short SRT, and then using ceramic, running at a high flux. Okay, these are new approaches, and then using ceramic for industrial application. All right, and then okay, another interesting topic is using membrane under anaerobic condition. So this is to produce high effluent quality, suspended solids free, but ammonia is still very high. So you produce biogas for energy production. So this permit, what can you use? You can use for agriculture irrigation, microalgae cultivation, and even people look at nitrogen removal via NMOX or adsorption, phosphorus recovery, and nitrogen recovery. And then your digestate can use for fertilizer. So this is, there's an increasing trend of using anaerobic MBR for energy recovery and resource recovery. Okay, so you can achieve energy neutral and high value products recovery. So this diagram just showing that moving forward in future, anaerobic membrane bioreactor can be carbon offsetting energy recovery compared to your activated sludge with anaerobic digestion. Okay. Okay, membrane fouling control. Of course, R&D look at pre-treatment, surface modification, maybe more hydrophilicity, more hydrophilic, more oxidative treatment, chemical cleaning to remove foulant. And then people look at the effect of chemical and humpback straws, how to minimize the impact. Okay, and then recently we also study a lot using chlorine quenching, cell-to-cell communication, telling the bacteria, okay, don't attach on surface because there's this bacteria producing this organic signaling molecule to attach to surface. But now you put another microbes in to consume this signaling molecule, then you can reduce the membrane fouling. All right, so this is MBI and a little bit on the nitrogen removal and biogas recovery. So this is the MBR. Okay. All right. Let's see any questions from the students.
Okay, Professor Ang. So yeah, for the question, yeah, if you have any question regarding the membrane, yeah, maybe it is relatively new technology in Indonesia, despite it's already well known. But I have a question, Professor Ong, because recently mostly in Indonesia, the biological treatment process is just using lagoon, and some of them using extended aeration. And recently, to increase the MLSS, our government and some of consultant came, and then they add the biofilm carrier using like media, coldness, maybe coldness, yeah. So so to increase the MLSS. So my question is, yeah, maybe for the operational cost, the coldness is more cheaper than membrane, right? But how about the MLSS itself? It is membrane is not comparable or powerful enough, or what do you think?
Okay, in my opinion, you use the MBR is when you have land space constraint, and at the same time you are looking at water reuse. Okay, then it makes sense because once you touch membrane, the cost is high. So if you are purely looking at simply like biological treatment, okay, they call it MBBR, moving bed biofilm reactor, putting a carrier to increase the bacterial concentration. This is a very good idea, so that you can improve your treatment efficiency. You produce a permeate, and then you can go through a good solid liquid separation. Even they are using fabric material for solid separation. You don't have to go to this polymeric membrane. Okay, then you can, after you go through even a SAM filter, you can produce a very good quality permeate that can use for water reuse, but of course not for consumption, but more for like irrigation, for farming, you know, that kind of usage. Okay, but not for drinking purposes. So I certainly agree with you that MBR membrane process is not, it should not be applied blindly. You know, you must have a purpose for it because it is very costly. When you touch membrane, any membrane processes, it is costly. So to use that, there must be a good reason for using it. Okay, so that is when you do water reuse or high quality water reuse. Then you need a membrane process, a membrane. Otherwise, there are cheaper alternatives. Okay.
Okay, another question, Professor, but for the drinking water, I think in membrane technology is very interesting, especially during the disaster event like in Indonesia. We have sometime like a flood or in the disaster. It's, what do you think?
I truly agree with you. I think for water treatment, UF membrane filtration is a very, very good, reliable in terms of the water quality. Especially in, like what you say, when you got flooding, the turbidity is very high. You do not know whether the pathogenic compound. So you have all these membrane filter system. You can produce a very high reliable quality water. And then if you say I worry about the water quality, put a GAC, okay, activated carbon. Then you will safeguard your water for safe drinking water purposes. So certainly, if you ask me, what should we move toward membrane? Maybe more of the drinking water rather than wastewater treatment, unless there's a motivation for you to use for water reuse. Otherwise, it's very costly. Okay. Yeah.
Okay, it's clear enough. Thank you, Professor. Okay, I invite Mas Maulana Nurul Yahya. Please, you can unmute your mic. Okay, you can ask Professor.
Right. Thank you for the opportunity to allow me a question. So, good afternoon, Mr. Yong. And it was mentioned earlier that the water treatment plant, including the membrane reactor, costs a lot of money. So, and I'm curious about how do you deal with the very high cost? And I'm curious about how do Singapore, how do that all members of the community of people in Singapore can reach the cost of providing clean water treatment like that?
Okay, so if you come to wastewater treatment, you have to be mindful that usually the public, okay, they do not know all this technology. Okay. So what they care is how much I'm paying for my water price. Okay, so the key, that's why I say always the challenging part is how much are you charging the water? Right? But this world is very interesting because people never complain about electricity price going up. They are not happy, but eventually they will pay for it because they will say, oh, oil price increase, energy price increase. Now, because of this, petrol price increase, oil price increase, your electricity price increase. So people, you have to pay more. But they think, still need my handphone charging. I cannot don't use, right? So people will pay. But of course, some people, your price too high, they can go demonstration when you hear a story like this. But when you come to water, how in Singapore, because people are paying for the water price, okay, they're paying the water. So of course the government have to invest money in the infrastructure, but at least the operating costs they are recovering back. Okay, they're recovering back the water operating costs from the water price, and then they also doing some of the capital recovery, but through long term. All right. So to answer your question is that the key is still in the water price, and then that is very political, right? So you have to convince that water treatment is not cheap, but this is, of course, it depends from society to society. What is the affordable range? So in Singapore, water price just now I show you is not cheap, almost $2.70 per meter cube. So that includes the wastewater treatment. So that has been factored into the treatment cost, because in Singapore, why they move towards MBI, because by switching to MBR from the activist side, the treatment capacity increase. Okay, so now you can expand your treatment capacity instead of using more land. Because Singapore land is so expensive. So I convert to MBR, I can treat more wastewater with the increase of waste population or increase in wastewater flow. And then I still produce high quality water for new water production. Okay, so everything factor into the saving in terms of land space. Because Singapore land space is so expensive. All right. So in Singapore case, there is a justification to move towards membrane barrier. Okay. So I hope I answer your question.
Is it clear enough, Mas Yahya?
Yes, it's
Okay.
clear enough, and thank you for your explanation.
Okay, I invite another student. If you still have a question. Yeah, Almira Nul Amalia, please.
Okay. Thank you to Mr. Awal to give me a chance to asking a question. So I want to ask a question. First from all, thank you for the detailed explanation of the bioreaction membrane technology. It's really great to be in the same forum with you, Mr. Ng. Sir, I have a question based on the graphic data presented. Several countries use this MBR technologies massively. I believe it is because of its high level of effectiveness. But is there something that catch my attention, namely how the impact of this technology on the surrounding environment, how the condition of the land or waters around it? Because at least I understand if a technology that produces a large amount of energy, of course, it requires a large amount of energy as well. So, sir, please explain the explanation. Thank you.
Okay, so yes, you are right that energy cost is higher than the conventional wastewater treatment. So if you look at all these countries, when they go for all this MBR, they have the water reuse in mind. Okay, when they produce this reused water, they are selling the water. Okay, so selling the water is also a cost recovery. All right. So that is the motivation because of water reuse. And secondly, it's also the stringent discharge limit, especially in the Midwest of the US. Okay, there was a time they increased the discharge standard. In order to achieve the standard, they switched to MBR so that they can have a consistent treatment performance. So to answer your question, you find that a lot of these countries, when they implement, they have a certain purpose in mind. They just don't implement blindly. There was a driver for it. Either stringent environmental discharge standard, or they are generating reused water for water reuse. So they are producing water and selling this water or recovering this water, which has a benefit. So nothing is, everyone you say nothing is free. You want better water quality, you have to pay for it, but you recover the cost because you produce recycled water. Okay.
Okay, it's clear enough.
Yeah, it's very clear. Thank you for your explanation, Mr. Ng.
Okay, maybe the last one, maybe. Is there any question you want to ask? Yeah, okay, maybe the last question, Professor Ng. If in Indonesia we have also like activated sludge, yeah. Yep. If we want to, I mean, but this is in industry. Yeah, in industry, I believe the land requirement is limited. I mean, land available is limited. So
Yeah.
which configuration is better, whether using in the aeration tank or side stream membrane?
Okay, so it really depends a lot on the industry situation. If you ask me, side stream is also possible. Existing stream is also okay. So there's really different option available. So there's no one magic solution. All right, and certainly MBR with the water reuse in mind is a very good possibility, especially for industry. Okay, and then but like what I say is that there must be motivation, because usually industry will not want to spend more money. Any business, they say their objective is to maximize profit at the minimum cost. All right. So why should they implement water reuse unless there's a water shortage, right? There's a water shortage, or there's a government policy that required the company to do water reuse. For example, in Taiwan, the semiconductor, if they mandate 80% water reuse, right? Then because of that regulation, the factory has no choice except to do MBR, RO for water reuse. So if you ask me, in Indonesia or any other country, there must be motivation. Either there's a shortage of water, or the water cost is very high, or there's a shortage of water that they force them to go into water reuse or desalination. So that is my answer to you. So it really depends on the locality, place by place. Yeah.
Yeah, because currently in Indonesia there is a regulation that force the industry they should because the river pollution is very high, so the government like push the industry to inject the water into the soil. So the industry should change their wastewater treatment process, maybe like a membrane or using post filtration to attain the required water quality level.
Yeah. So I think that is good because all this need government policy. Otherwise, factory will not do it unless there is a regulation. Yeah. Right.
Okay.
Okay.
Professor Ang, thank you so much for your explanation. Yeah. Maybe if it is not the pandemic, actually, this is our plan, because we sometimes we want to how to say, like a study tour. Yeah.
Oh, okay.
We want to really want to visit the new water reclamation plant in Singapore, and then. Beside that, we can also go to Marina Bay Park, or we go to Merlion, and then beside that we want to visit it. So maybe I hope that our cooperation will be last, and then if we decided to go to Singapore, please allow us to get your support, or
Sure. Yeah, let's keep in communication. All right, thank you.
Okay.
Thank you. Yeah.
And also because Professor Eko didn't have opportunity to say hello, so he said to me that please say hello to Professor Ang.
Okay. Thank you.
Thank you so much, and please give virtual applause to Professor Ang. Yeah.
Thank
you so much.
Thank you. Yeah. All right. Okay. Bye.
Bye. Yeah.
Bye.
Thank you.
Thank you. Bye.
Baik, itu tadi ya kuliah tamu dari Profesor Ang, dan